Hello and good day. My name is Yusuf Abubakar Sha'aban from the Department of Electrical Engineering at the University of Hafr al-Batin. I'll be presenting my conference paper to you titled The Automatic Tuning of Model Predictive Control Using Genetic Algorithm with Historic Process Data. Now, there is this argument that the current control approaches are not flexible enough for future industrial needs. So there is a need to move to more flexible control approaches. Now, a survey amongst industrial practitioners revealed that PID, model predictive control, and system identification are the three most successful industrial control technologies. PID, particularly PI, accounts for over 90% of industrial control loops. This could be attributed to its ease of implementation, its history, and it works for most processes. However, because of this, it is often applied even on non-suitable processes. Now, model predictive control, on the other one, has been the most successful advanced control scheme over the past few decades. However, based on, if you compare with the performance achievable by MPC, we still feel it has relatively limited industrial application. This could be due to some factors, including the need for expert knowledge, its unavailability in off-the-shelf hardware like PLC. PID, for example, is found in PLC and other off-the-shelf hardware, and you just need to configure it. But for MPC, you need specified dedicated PCs, which you have to tune and implement MPC. There is also a lot of cost associated with model development in MPC. System identification, on the other hand, is needed for most control techniques, especially model-based controls. However, it is also expensive due to plant downtime, disruption in plant operations, etc. Now, previously, MPC has been proposed as a replacement for PID in suitable applications. And we have proof from previous studies that a variant of MPC, the predictive functional control, showed promising results when practitioners were trained on how to implement and manage it. However, there is still need to address certain concerns, like the need for expert knowledge and the cost of modeling. Now, the cost of modeling could be solved by harnessing the vast amount of data stored in industrial databases. Some work has been done previously along this line, where some of the works focused on identifying data intervals that are rich, and informative for system identification. Other works looked at the conditions for closed loop identification from routine plant data. Some other works looked at automatic tuning of MPC and implementation on PLC. However, in this work, we are proposing a designing of MPC from existing PII controller and plant data. So the contributions could be looked at as follows. We formulate MPC design as an optimization problem. We thereby eliminate the need for expensive plant tests, and we also decrease the need for expert knowledge, while we achieve at least the performance of the existing PID, which could be improved by further tuning. We adopt this the framework where you have a controller in series with the plant and an output disturbance coming through a transfer function. The transfer functions for G, GD, and C are as given, and the respective polynomials are also defined here. We also adopt a first order system, as most processes can be approximated by their first order model. The discrete and continuous models are given as equation 1 and 2, and we can convert them using exact first order discretization or using the formulas for K and tau here to find the relevant values. Okay, so in this work, we are focusing on 4 main areas: identifiability from routine data, model predictive control, genetic algorithm, and PID. So the last two wouldn't be focusing on them. We'll focus on the first two here. Routine data could have sufficient information for modeling, and if we harness that, we could reduce plant disruptions. Now, stored data could either be in closed loop, therefore we need changes set point, or in open loop, where we just need changes in manipulated variable for these sets of data to be informative. Now, with rich data, prediction error-based identification methods have been shown to be sufficient to identify steady-state models. So also, we've seen from previous research that for a fixed model and controller structure, once the dead time L is large enough, then we could get reasonable models from routine plant data, and we'll be exploring this in this research. Now, model predictive control uses model prediction and measurements to solve a fixed horizon control problem. You obtain an optimal sequence of inputs and you just implement only the first element. So typically in MPC, when we have a controller running, this is how the process goes. So first of all, we take the measurement from our plant. Based on the measurements and our models, we make a prediction. And then we solve an optimal control to find the sequence of inputs that will give us the predicted output. However, we just take only the first element and implement that. After that, we take the measurements again, repeat the prediction, and the cycle continues. So this is a brief of how MPC works. In this work, we adopt the state space model with the change in manipulated variable. This is a good model to adopt because it ensures offset-free control. We also adopt the cost function that minimizes the error between the reference and the output, and also penalizes the change in manipulated variable. Now for the prediction horizon, we adopt the time to steady state of the process, which is 5 times the time constant from the dead time, and we divide by t to make it in discrete time. We adopt the control horizon M of 3 because previous research has demonstrated that choosing values beyond 3 does not give much in terms of performance improvement. Okay, so fixing these values result in us having a single tuning parameter for the MPC RW, and this also ensures that when we find our steady state gain, time constant, and theta, dead time for the first order model, and RW, then we can fully define our model-based predictive control. Genetic algorithm, on the other hand, is an AI-based evolutionary algorithm. It is very easy to use and has a good convergence speed. So it could be used to solve complex optimization problems, even the non-convex ones. So in our framework, we assume a PI controller with KP and TI, the proportional gain and integrate time. So given the data, we are going to try to find these parameters K, T, and RW, because the dead time could easily be estimated from the data. So what we do is we feed the data to the model predictive control, and then we get the output of the model predictive control. We compare it with the output of the PID controller, and we try to minimize the sum of squared error between the two outputs, while the GA returns the parameters that give the minimum sum of squared error. Once our algorithm converges, we can then use these values to design our MPC controller and compare the performance. Okay, we initialize the GA using these values specified here. Now, when we tried with the plant model here, the controller and the disturbance model, we apply D to be white noise with unity variance. We carried out 100 Monte Carlo simulations, each with 10,000 samples. And these were the results obtained. So this is for the gain, the time constant, and the tuning parameter RW. Now, it is clear that the blue line here is the true value, the green line is the mean value of this individual 100 samples. We can see that some of the samples is that 2, 77, and 94 here. They are far away from the mean value. The same values are far away from the mean value in all the other plots. So we thought, okay, let's use the cost function to try and discard these values that are far away, that are outliers from our results. After some simulations and looking at our results, we arrived at the value of 7.5. So any of those parameters with sum of squared error larger than 7.5 were discarded. And after that, we got these results where this was the mean before removing the outliers, and this is the mean after removing the outliers. And these values are close to the true values. So we've successfully designed our model predictive controller without any plant test. So in summary, in conclusion, we've developed a method of designing model predictive control from existing PID and plant data without any plant test. We use GA and Monte Carlo simulation to achieve these results, which are promising. However, there is need for more work, especially on the tuning of GA. We tuned the GA and changed the values arbitrarily until we got good results. So there is a need for a methodological way of tuning the GA. Secondly, teaching of the bias. Here we use the sum of squared error to remove some of the samples we considered as outliers. There is a need again for a more methodological way of solving this problem. Thank you very much for listening. Thank you.